Here's rule 1. You should pop as soon as possible. So pop, remember, is move from container to output. So if the thing sitting on the left of your container is the next thing to be output, you have to do that right away. Okay, this prevents you from just pushing in to the right of that, which otherwise you could do. And the second rule. So the second rule says that if possible, you must use a bypass. So if the first thing in the input is supposed to be output, you've got to bypass it. So those can never hit the container. And if you think about when this is possible, this is always when that entry is bigger than everything to its left. So it's a left to right maximum. So all left to right maxima have to be bypassed. That's precisely the entries where this rule will come into effect. Okay, and you can prove that if you follow these two rules, you generate every permutation precisely once. So now, if you go back to stacks and queues, there's this result that the number of 312 avoiders is the same as the number of 321 avoiders for every n, and in fact, that's the n-Catalan number. Forget about this part for a moment, that it's the n-Catalan number. If you just want to know they're the same, well, there's this obvious equivalence of the two machines. Because when we push something into either the stack container machine or the 2Q container machine, there's a unique place to put it always. It's either at the beginning or at the end. Okay? And if we're reading from left to right, we come across a left to right maxima of our permutation, we have to bypass in both machines. So not only do we see this equivalence right here, but using the restricted containers with these rules, rule 2 is going to ensure that we've got a bijection that preserves the values and positions of the left to right maximum. So we can do this via bijection. Preserving values and positions. Left to right maximum. There's other things we could do that would give us some similar results basically for free. If we take this stack, and instead of allowing it to be arbitrarily large, we cap its size, then that's like avoiding 1, 2 and avoiding k down to 2, 1. Okay, we're going to have a maximum size of that stack. Or similarly, we could make a maximum size on this queue. And clearly, we'd still have bijections. So we'd also get, with those, so if we're taking the maybe 1 to k down to 1 machine, and the limited depth 2 stack machine, okay. So the permutations that are generated by these two are in obvious bijection, because we just take the same operation sequences and do them on both. And we get the following equivalence. This and two classes are equinumerists. So this was first noticed by Chow and West. These enumerations are in terms of Chebyshev polynomials. But here we can just, if you think about stack sorting as deques, these are really just deques of height k. And we get this equivalence basically for free.
So this shallow theorem implies all these amazing results.
I'm not sure how amazing the results are. They're implied by a shallow theorem for sure. Okay, but what I haven't shown you is how to compute the stack machine is counted by the catalog numbers. Okay. Now, Dorota, I promise this won't take very long. Don't worry. This will be 5 minutes because you're not going to be very happy with how I'll do it the first time. Yeah. So if we think about this AB21 machine, so I guess this is two queues in parallel. We can think about it having two states, really. Either, so our rules are up there, either we're allowed to pop or we're not allowed to pop. And the way this works is the following. So, I'm just going to show you where we go, and we'll explain this. If we're allowed to pop the leftmost thing off the container, and we do a bypass, then we're still allowed to pop it off the container. If we do pop, well, first of all, we can only pop if we're not empty. Then we're still allowed to pop, because we were allowed to pop before. What happens, the reason we get into the can't pop state is that U1. If we push something new into the container, we said if we were going to be able to pop, we had to pop. So this means we can't pop anymore until we do a bypass. And if you're in can't pop and you keep pushing, you stay in can't pop. Okay? And initially you start in the can't pop state. Now, if we introduce generating functions, we introduce this catalytic variable u, which is going to count the number of symbols in the container at any given time. And x is going to count the number of symbols output at any time. And then we're going to count paths to the two states. So f will count paths to can pop. G will count paths to can pop. Then we end up with the following system of equations. Okay. We start in can pop, so that's a 1. Nothing is in the container or in the output. Or we go to can pop by doing a bypass from either can pop or can't pop. Bypass just takes something from the input and moves it to the output. Or if the container is non-empty, we're allowed to pop. Pop replaces, well, it puts something in the output and it removes something from the container. Okay, but we have to make sure that we're not popping from an empty container.
So is that a G there?
Yes, I'm going to let F be the count paths to can pop states, and G count paths to the can't pop state.
So now the equation is coming up.
Yes. So that's can pop. Okay. How do we get to the can't pop state? Well, this is easy. If anytime we push from either state. We go into the Cantor state. Push adds a symbol to the container. So that's adding a U, and everything else stays the same. Okay, so you set up this system of equations, and you solve it. You see that really G is U over 1 minus UF. So you can eliminate G, and then you get an equation in F of x U and F of x 0, and you can solve this with the kernel.
No! Stupid method.
I told you it's like this.
Empirical yet rigorous method.
Yes.
You crank out the first
So-
50 terms, you get an algebraic equation, and then you verify.
So here's what Dr. C would like me to tell you to do. Instead, don't do this. Take these equations and generate hundreds of terms, and then guess and check.
Excuse me, for this trivial case, it's 30 or 40, so right.
I think it's even less. So if you take these, we can generate all the terms we want. We can see that if we knew, since we know G in terms of F, that goes up here to say, if we can guess F of x0, we can actually solve for what F of xu would be. Okay? And if we can plug all those in and satisfy these equations, then we've checked it. Okay? So we can do this all empirically. We don't have to use the kernel method.
Yeah.
Okay? Good. That's what you want me to say. So, there's this topic that's come up, enumerating these so-called 2x4 classes. The 2x4 because we're avoiding two patterns, both have length 4. Okay, and the reason these are interesting, well, the reason people are interested in them is that if you avoid one pattern of length 3, it's always the Catalan numbers. One pattern of length 4, there's 3 cases, and one of the only one that's not solved looks very, very difficult. So you add on more patterns to make it easier because you're avoiding more stuff. And if they're both length 3, it's too easy. If one is length 3 and the other is length 4, it's still pretty easy, so we go up to both being length 4. There's a lot of symmetries of this pattern containment, so up to symmetry. There are 56 cases. Up to enumeration. So I'm going to identify two classes if they have the same enumeration. We actually know this fact that up to enumeration there are 38 cases. So we know we're going to get 38 different generating functions.
Are they all in the OAS?
Yes, of course they're all in the OAA, yes. And of these, all but 3 are now enumerated. So this has been a lot of work by a lot of people to get the 38 down to 3 that we don't know.
And you still don't know, even after this talk.
We still don't know the 3. What I want to do first is I want to make 2 points. Of these, I said symmetry. Well,
Can you write them down?
I go on one. Okay. So I said there's 38 enumerations. 10, well, of these 56, 10 of them all have the same enumeration. And that's the Schroeder numbers. Okay. Of those, 6 are restricted container machines. So, I should say it was Darla Kremer who proved that there are 10, exactly 10 counted by the Schroeder numbers. Let me show you what the containers look like. Okay, so for a stack, I do a single decreasing line. Here, we've got this capital alpha. So it just means we have to be an increasing subsequence, an increasing sequence followed by a decreasing sequence. These are the 3, 1, 2, 2, 1, 3 avoiders. So this is the class that avoids 4, 3, 1, 2, and 4, 2, 1, 3. Okay, also for B. Also, we let our container contain these layers. So a decreasing segment below and to the left of other decreasing segments. That, or 2 more cases. That's what all the containers look like. Now, once you show that one of these is counted by the Schroeder numbers, it's trivial they're all counted by the Schroeder numbers. Because if you think about what we can do when we push into containers that are restricted like this, if the container's empty, there's only one thing we can do. But if any of these containers have at least one entry, there's 2 places we can put the next entry. Okay? Here, maybe the V is the easiest way to see it. We can put the new entry on the beginning and the end. In the alpha, really there's a maximal entry already in there. We can put the new one to the left or to the right. Here, we can add to whatever decreasing segment we were building or start a new one. Okay. Here, again, the same thing. We can add or start a new one, add or start a new one, and add or start a new one. Okay. So there's always 2 things you can do to a non-empty container here when you're pushing. And therefore, we get exactly the same as we did with the stack and the 2 queues. We get a bijection that preserves values and locations left and right next. Okay, so the last thing I wanted to point out is these 3 that have not been enumerated. They're the following. Avoid 4, 1, 2, 3, 4, 2, 3, 1. Avoid 4, 1, 2, 3, and 4, 3, 1, 2. And avoid 4, 2, 3, 1. You'll notice that all 3 of these start, all the elements we're avoiding start with their largest entries. So these all come from restricted container machines. Which means we should be able to use the guess and check approach, except when we go, we can generate 1,000 terms of each of these enumerations, but we can't guess anything. Okay, so we can't check it. Okay? And I'll give you an even better one.
I mean, you cannot, but somebody maybe.
The computer can't guess it. So
Not yet.
So for all 3 of these, we have 1,000 terms and can't guess a generating function to it. The intersection of these 2 here we have 5,000 terms, and we can't guess any sort of generating.
So this is still officially open.
This one is still open with 5,000 terms.
Is that in the OAIS?
I'm certain this is in the OAS, but I don't have the A number on me.
Do you have the A numbers for the other three?
Not on me, sorry. Let me just double check.
But there's a paper we can refer to.
Yes. This is paper. And you can also just get a few numbers. Oh, I'm sorry, I do have them, so I can tell you after. Thank you.
Thanks for a great talk and for intriguing homework problem. And we'll be glad to answer questions in private, but please let me know whether you can join us for dinner. Now, it's 10 here. Thank you, dinner.